It's 8 o'clock.
All right. Good morning. Can you hear me?
Yes,
Yeah.
Professor.
All right, perfect. Thank you. Thank you. All right. So a couple of things. Yesterday I assigned the new homework, both the individual and the team homework last night. And so today we are going to have the last lecture on electrostatics, and on Wednesday we are going to move to magnetostatics. So I'm trying, so two things I have to tell you that I have realized. Because of online, we are a little bit slower in moving in this class. So we're not going to necessarily we'll do only the critical topics, I have to say. Also, the 1 week we missed and so forth was problematic, in addition to just understandable, of course, is that online does not necessarily provide the same environment. And I have noticed that there is more difficulty in following some of the topics compared to, like, say, last year, for example, at least even half of the spring semester where we were doing the same class. But in any case, we'll do the best we can, obviously. So the other thing is, in response to some comments I received, it is true that April 2nd is a Friday and is a reading day. The reason I had not indicated as a reading day is because as we were going through this week that we missed, I got some multiple messages from the university. In the beginning, was at least to faculty, in the beginning was suggested that this reading day is going to be we are going to have to lecture during that day. In any case, at the end, of course, you're right, that has remained as a reading day. So you will notice that I will have to move some material. So to really, because the changes that I've made up front, I assume that day will not be a reading day. But in any case, it is according to the university calendar. So I'm going to change them and diffuse the material in the rest of the class, what we were supposed to cover that day. And the other thing that I believe some students wanted me to discuss, which I believe I did in the beginning, but I will do this again, on how we're going to get the bonus system to work. So here is how the bonus system works, at least in my grading scheme. On the basis of everything that I gave you, so let me start from the beginning. When I put the schedule together for the class, before the class even starts, I take the most optimistic view that nothing is going to be missed, that every day we'll do the right thing. I mean, that's the only way I can do this, all right? Assuming that the semester is going to run the regular way. And then we are not going to have delays or anything. I mean, I assume that, like, we move. And I then have an estimate of how many homeworks I'll give, how many exercises, quizzes, and so forth. And then I set the place for the midterm, and then the final is always set by the university. So obviously, when we are to go back at the end of the class, when I am to get grades and find what is the peak grade, the peak points, like the maximum number of points accumulated in the class by anyone, I only look not at what I estimated, obviously. That was my initial estimate in the beginning of the semester, but on the actuals. So I'm looking at all of the points that all of the students have accumulated and the maximum number of points that have been accumulated without bonuses, just the bare points for everything we've done. That is the maximum number of points for the class. Then I give a grade on the basis of that. And I have already provided in my notes under orientation how the grading is going to be divided. Assuming always at that time when I do this is at the maximum that I estimated in the beginning of the class. But more or less something similar is going to happen, like in terms of separating the maximum point from the minimum point and how I'm gonna do the grading in between. Then after I do this, then I add all of the bonus points to every student who has gained bonus points. And then I see how the bonus points move these students up or up the scale. And then I change their grade from the original without the bonus points to whatever grade they're gonna have with the bonus points. Is that clear? How am I doing it? Any questions about that?
I think we're wondering, what can we do to get bonus points? Where do those come? Where do we earn those?
You earn the bonus points, for example, and also it is described. The bonus points go as soon as you go to 75%. So practically, here is how I constructed the bonus points. It's not extra work. It's like achieving with the work that I'm giving you. So if by the end of the class, you have achieved 95% of the points in its category, of the points we truly accumulated, not the estimate, but the truly accumulated points, then you get the bonus for 75, for 85, and for 95. If by the end of the class, so you see how you go, and these are in fact some bonus to help you move ahead and do the work. And do the work along the way, not to do it at the end of the class. So bonus points, the way I'm giving them is to encourage you to study along the way. So as soon as you go to 75% of the maximum number of points that we would have in the class, and I will give you, in fact, if you regularly do your work, that's all that I'm saying. If you regularly do the work, as soon as you go to 75% of the maximum of that work that I have given you, so you can regulate and see how far you are. So for example, what I would do, say we have 3 homeworks so far. How have I done in respect to 3 homeworks? Am I above the 75%? If you were above if you have consistently stayed above the 75%, then you know you're gonna get a bonus. If you consistently stay above the 85%, you're going to get a bonus, an additional one. If you then come out to be above 90 or 95% of above, then you're going to get the 3 bonuses, 75, 85, and 95. And that's how it applies to every category: homework, exercises, quizzes, and I think that's it. And also team homework. So the bonus points, I designed them like that. And it's based on my philosophy, which I think is founded on some real evidence, all right, some science, that says that you don't learn by trying at the end of the class to overexceed yourself. For example, my theory is that if I take 2 students, 2 of you, or the same student, say, let's assume, maybe let's take 2 students who are equivalent and in their understanding of the class, all right? And then in the foundational base. So one of them spends every week or every day, half an hour, for example, 15 minutes, whatever it is, half an hour every day. And the other student spends like 5 hours at the end of every week, or it may spend 2 full days and nights before the midterm or before anything else. Then I tell you the student who spends consistently half an hour every day throughout the class is going to do way better than the other student who spends periodically an immense amount of time for the class. The student who spends time every day, even a little bit of time, is going to do better than the student who kills himself or herself before the major things, like at the end of a homework, for example, like a few hours before the homework, or a few days before, a day before the midterm, or like 2 days before the final. So 2 hours distributed on every day versus 2 hours spent in one time, the 2 hours distributed have a much better impact on your learning than the 2 hours spent all at once just before an event. That's the theory. And that theory has been proven on the basis of how the brain works. There is a lot of neuroscience that has taken place in the last 10, 15 years. Okay, so that what I recognize and give a bonus for is the ability to stay along the way. So even at 75%, that some other faculty will consider it a B, I give you a bonus for that. And why do I give you a bonus for 75%? Assuming that there is somebody who has done 100%, that's how I measure it, all right? Your 75% is gonna be measured against the student in the class who has done 100% consistently. So that's how you consider not at my 100%, but somebody else is 100% achieved 100% consistently. Your 75% is going to give you a bonus. And that is the reason I'm doing that. So that's how you're going to get the bonus. I'm not going to give you bonus by asking you to do a little bit of work here and there. What I will do is to give you an opportunity to make up for lost points. So we will have 2 makeup assignments, only for those who have valid reasons to miss the points. All right. And I have a number of students who have really indicated that. So 1 makeup assignment is going to be immediately after the midterm, because I want to see whether somebody for health reasons missed a midterm, or if, and another one is going to be just before the final. And there will be take home assignments. They're not going to be like an exam. I will give you something on a Sunday from 1 to 3, and I can regulate it from Canvas to be available from 1 to 3. And then you will do the work, upload it, and that's it. And you will see how we are going to do the allocation of the points. Any questions about that?
Considering we missed like that 1 week due to bad weather, which is essentially 2 top hat assignments, a quiz, a homework, and a team assignment. Mm-hmm. So we're still basing it off of like the top end grade, or
no? Hear me what I said. Maybe I cannot articulate that very well, and I apologize for that. What I said is the following. Now let's draw the line right now in terms of time, all right, and see how many homeworks we've had, how many exercises, how many quizzes. You will take those, take the maximum that goes to each one of them, maximum points, and that would be the theoretical maximum up to now, okay? And we have missed many things, but I don't count the things that we have missed, obviously, up to now. Now, even that is theoretical, because it is possible that if what I'm giving you is extremely hard and nobody makes it to that maximum, then I will look at the student who did the highest number of points in the class, and that will be the maximum. In your class is a little more complex because you have honor students. So usually I remove the honor students and I grade them separately, and I give them also some extra work along the way. You will see that some of the homework, either individual or team, are for honor students. So I will not take an honor student's maximum and impose it on everybody else. They are a separate class. So class meaning a group. So I'm looking for the rest of the students. The one who did the maximum in the class up to now, that will be the maximum I'm working on. Is that clear?
Yes. So, for example, I'm in the honors section. Would it be the max amount of points for the person who's in the honors section?
Exactly. Yes.
Okay. Gotcha.
Yes, of course. It's always because that way I take away, my experience tells me, I have to take away a number of factors that may impact your grade, which are not under your control. If, for example, I keep giving you things that are above what you should have, or I am a human being, sometimes I give you a difficult problem, it's everything, it's subjective to me. And people make mistakes or make assumptions. Let's assume that I gave you a very difficult problem and nobody was able to solve it. I'm not going to penalize you for not being able to solve a very difficult problem that was not appropriate for you. See what I'm saying?
Yes.
I assume that the class has very smart students. That's my assumption. I assume that all of you are extremely smart. And the only thing that I take as a variable is the amount of time that each one of you places in this class. And I have to tell you now, since we're talking about this, and we're not wasting our time, even if now it's 15 minutes, but I think it's important discussion, especially because I don't see you, all right? And I have that feeling that there is a gap in our, I just at least feel it myself, you know, I have this sense of a gap between my relationship with the students because I don't see you, you know, practically now that I speak, I see myself. I don't see anybody else, which is unfortunate. But in any case, what I wanted to say is that, what did I meant to say for this class? That, there is one thing talking about students. You know, I have, here it is. We have 3 lectures a week, and I have 2-hour office hours, 2 hours of office hours every day. I do it for both sections, but I have to tell you, there are days of office hours where I am by myself and where automatically Zoom kicks me out because if there is nobody for 40 minutes, it goes down. So, all right, so I'm just telling you. I'm giving you 6 hours of office hours. We have 3 hours of lectures. And I have, as part of these office hours, solving problem, which in fact I have to say, I'm very pleased to see that the number is increasing in the problem solving session. And then specifically I have office hours on Sunday because despite everything else I'm saying, I'm a person that I have been a student myself. I did not get a PhD without being a student, obviously. I know the pressures. I know exactly what I was doing, which is everything that I tell you not to do because it did not work for me when I was doing that. And so I know how life is. So I put the office hours from 1 to 3 on Sunday. Okay, a lot of students come, but I have to tell you this. Sunday night at 9 or 10 p.m., I am going to bed, as a matter of fact, because I'm exhausted. I'm working on Sunday from very early in the morning until late at night. And I get emails from students who say, could you explain to me something fundamental about the homework? What am I going to do? How can I help the student? On one end, I have to tell you, my human side gets really angry. But I have, in my age right now, I have managed to control it. So then I go back and say, okay, I understand a lot of things can go wrong with this person. Maybe something went wrong the whole day, all of this. But how can I help somebody at 10 p.m. on Sunday night when the person says, I have no idea how to solve the problem. Could you help me? If you were in my position, how would you help this person? How in the world would I be able to help this person with email? I cannot even type equations on an email. I look at my email from my bed, for example, or somewhere ready to go to bed. I have my iPhone and I look the email. How can I help this person? So that's what I'm saying. I will do the best I can to have you do the right thing, considering all of the distractions and all of the problems that exist there, which I know. I raised 2 children, I have grandchildren. I know everything that goes in life. I'm not like a person who is does not understand or who lived under perfect conditions. I did not live under perfect conditions in my life. I'm an average person, obviously. I acknowledge all of the problems, but at the same time, you need to help me so I can help you. Help has to go both ways. It's like somebody's drowned. If you don't extend your hand so somebody can grab you, how are you going to help yourself? You need to extend your hand to me so I can help you. And that's what I wanted to say, because this is not rare. If there was to be one case here and there, I would not complain. But this happens every Sunday, and it happens by more than one people. So please try. I know it's difficult to control your calendar. And if there is anything we learn in life is how to control our calendars. But please put some time every day on your calendar, good or bad, for half an hour even, not very much, just half an hour to go through the material, because you're going to see you're going to have to spend less time. You're going to have even more time. If you read something, the homework on Monday, and then you know that you don't understand anything, then you have an opportunity to approach me, and I can bet you anything, I can promise to you rather, that I will do everything I can to help you. But when you come the following Sunday at 10 p.m. to ask for help, then I'm afraid I will not even be able to respond to you. Because I don't know. In fact, last night I did respond to the person and I said, go and check, because this person, I don't remember what was the person, even the name. But the person asked for help about how even to think about the problem for the homework. And at 10 p.m. I said, or 9 p.m., whatever it was, 9:30, I go and check the solution at the third problem that we discussed in the problem solving session. That was the most I could do for this person. So in any case, I think said enough. We don't want to miss more. We have already missed a lot. Any other questions now? Do you think that's reasonable what I'm saying? Or you think it's totally out there?
I believe it makes sense. I think you're being pretty fair.
No, it's I just want to make sure, because I'm a human being, I make mistakes. Sometimes I have all the same feelings you guys have. I get arrogant, I get hard, I get upset, I feel sorry for many, it's like I'm a human being. I have all the emotions that each one of you has, but I have more experience to be able to try to control them, because that's what makes us better people, all right? You cannot change human nature, but you can educate ourselves to control the bad aspects of it. So I'm trying, but I understand that I can make a lot of mistakes. I can have some unreasonable expectations sometimes. That happens to me more often than not. And I try to moderate this. So that's why I'm asking you. I'm not asking you because I want you to, and thank you for giving me feedback. I'm asking you because I expect you to say, no, sit down with me and help me figure out how to help you. If you give me some positive guidance, and that's why I'm going to send you today this survey, because it can allow you in an anonymous way to give me guidance. All right. If you give me guidance, then I can promise you anything. I can promise you that I will do everything I can to accommodate the changes that you feel are appropriate. So that's what we're going to do. So we're going to promise each other we're going to be open. You're going to be open to me and I will be open to you. That's at least we can do on an online, all right? This online is horrible. I have to tell you, it's not good for undergraduate education, at least not part of the faculty. I don't know how you guys see it, but for me, it doesn't work. Okay, so unless there are any other questions, I would like to proceed with the material today, if I may. We're okay? Okay. I will assume that this is a yes. I need to find a pen here. Right. I lost my pen somewhere. All right. So in any case, I don't think we have, I don't know what my pen is, by the way. Okay, just a second. I just forgot my pen. We are going to go through this, and I don't believe at this point that I will need a pen for that, because it's pretty well. So here, I will share my screen. Share screen, but I don't need where the pen is. Now there it is, found the pen, thank God. It's all white and it's mixed up with the paper I have in my desk and it's very hard to see. Okay, so now we are gonna start with talking about, in a compressed rather way, we are going to talk about air dielectric interfaces, and we'll do some more examples on capacitance. Last time we did speak about the capacitance, all right? And we did talk about capacitance, which is a very important circuit concept. And we talked about the capacitance in a parallel plate waveguide. Now, what we're gonna do is introduce boundary conditions before we go and do some more complex problems. And why do we need to introduce boundary conditions? Because a lot of times in the problems that I gave you, you have more than one conductors, two parallel plates, for example, or even a coaxial line that we did like this, an example. If you have more than one conductors, in reality, you need to have a material to place in between them to keep them in place. And so materials are very important, obviously, and we need to understand how to treat them. There are two equations which are extremely fundamental when you have an air dielectric interface. And here I took a very arbitrary interface. So I assume that the blue is one material, and I assumed, as a matter of fact, that this material extends, so it's like here. So I assumed it extends down here, all right, that it does not stop necessarily there. But it is the upper interface between the material and the air that is of interest to us. And when you are to apply boundary conditions, you apply boundary conditions at points. So the boundary conditions are relationships between the fields from one side of the interface and the field from the other side of the interface at one point. So for example, when I look at this point here, all right, I'm at that point on the interface. First of all, I define two very important vectors, and they are unit vectors. All right, one is the vector at that point of the surface. The surface can be like this, the interface rather, which means if it's curved like that, or even curved like the way you see up here in the example, that means that every point I will have a different direction for this surface. The direction of the surface changes with location on the surface, on the interface. So obviously, at every different point, I will have a different direction. So here at this point that I selected as before, and I will make it red so you can see it at this point, I consider the N direction, which is the direction of the surface. So the vertical, the normal direction to the surface, that's the direction of the surface at that point. And in addition now, I consider the tangential direction to this surface at this point. These are the two unit vectors, which are extremely important. What are the boundary conditions now? What I say is this: if I am on an interface, on a surface, on an interface between two materials, one is down here, and then one is up above it. Then let's assume that I have somewhere a charge. And let's assume that I have a positive charge here. This positive charge is going to create an electric field. So this, what I'm drawing here is a very generic problem, as it is up there. But let's assume now what I decided to do is to show you exactly what the interface does. So initially the charge is going to create this electric field. Without the interface, if I were to take this away, cut, for example, then the charge will create a field in the same in all directions. So practically, I would say this one would be all the same, all right? I'm going to do that so you can see all of them like that. We have seen this problem. Now, what I do, I place this interface again here. And what that interface will do, if we have an epsilon here, epsilon, if we have an epsilon naught here, let's assume that it's air, an epsilon 2 here, or epsilon 1 and epsilon 2, just so we are similar with the other. The field is going to be affected by the presence of the interface. And how is it going to be affected? Two things will happen. First of all, the ray that comes like, let's assume that I have a ray here of electric field that comes here at this point. What is going to happen when that ray, if you could imagine it in time, all right, let's assume you see this ray slowly coming down, and then until it sees this interface. Never happens like that, but let's assume, because it's static, all right, there's no time, but we just try to visualize it. So it comes here, and when it comes there, at that point, two things happen. First of all, we'll go back here to these two equations. The normal component of the electric field, of the electric flux density, will go through without any change. All right, so here, for example, that is almost normal. That place that if all of these are rays of the flux density, okay, of the flux density vector. So this, which is normal, is going to go through the same way as nothing happened. However, if I take another of these rays, and it's this one, and this ray comes here, then obviously it hits the interface at in a different way. So if we were to consider at this point the two components for this D, one component would be a normal component, and the other component would be a tangential component to the surface. The normal component to the surface is going to go exactly the same way, it's not going to change, but the tangential component to the surface is going to change. And the tangential component is going to change because what we have from here is that D tangential equals epsilon 1 E tangential 1, and D tangential from the second medium is going to be epsilon 2 E tangential 2. And therefore, because the two E components have to be identical, that means that the tangential component of the flux density in medium 1 is going to be equal to, let me see, E2 equals to D T2 in the second medium, but divided by, multiplied by epsilon 1 over epsilon 2. So for example, when epsilon 2 is more dense, so it's higher value than epsilon 1, that means that the tangential component is going to become smaller. What happens if the tangential component of D becomes smaller? Inside the medium, then this is going to be smaller, which means that the material is going to bend down when it comes in. All right, so this component of this ray, rather, is going to continue inside the medium at a different direction and with a different value. So that tells you that when you have dielectrics and then you have sources above or below, then the direction of the flux density and eventually the direction of the electric field changes. And as you go from less dense to more dense media, also the direction, in fact, becomes well, it changes as you see here. As it comes, the angle becomes more narrow with respect to the normal. We will see this again towards the end of the class, especially in electromagnetic waves. So the only thing I want you now to remember is that the dielectric interface changes the direction of the electric flux, and therefore it changes the direction of the electric field and its value, obviously. But how it changes is very well determined practically by these two equations. That the normal component of the flux is continuous, but only the tangential component of the electric field is continuous. So instead of doing the epsilon1 over epsilon2, ratio that you see here, instead of remembering that, which is going to be more difficult because you may get more confused about which epsilon is in the numerator, which epsilon is the denominator, what we really do is to look at the value of the normal D and the tangential E, and those two are continuous. Okay, so this is what we learned from here. Now, if the lower dielectric becomes a conductor, what did we say? That the electric field inside the conductor is 0. We said that before. So practically the only important relationship that you need to remember, in addition to the fact that the total field is 0, is on the surface of the conductor. The condition that you have to apply is this one, which says that as the conductor changes the total original field that will be excited, say, by the point charge, what it does when you have a conductor and a point charge is that the excited field that is modified by the conductor, so the tangential electric field component on the surface of the conductor becomes 0, but not necessarily the normal. So what happens is interesting, all right? So if I have here a charge, if I have a positive charge here, and if I have an interface, let's say, that looks like this, flat for a second, and then here is conductor. So everywhere here, the field is 0. Then the rays that come from here originally, all right, they will look like this if that were to be alone. But when they come to the conductor, what happens to them? Since the tangential field has to be 0 here, they will come and eventually they will deform, so they become vertical. You remember what we said? That we have said this, but now we see it in view of the boundary conditions or the dielectric interface. So all of the lines from here will eventually terminate to be vertical to this conductor. So they will look like this. You remember when we were saying that, when we looked at shielding, that all of the lines will go vertically? That's what it is. So now we saw it as an outcome of the boundary conditions we said before. Okay, we did this, the parallel plate capacitor. I'm not going to repeat it here. It's for your, to review it, to remember it, but we did this solution, all right, in previously. What I would like to do for you, yes, go ahead.
Do you mind scrolling up? I didn't finish the notes. Yes, ma'am.
Yes.
Yes, ma'am. Thank you so much.
It does take, I will put them also on all of these. I will reload them.
Okay,
with
perfect.
my
I'm
notes.
finished.
Right, perfect.
Thank you.
You're welcome. So here, yeah, 3 examples and a very interesting on how the first one, of course, it's easy. The first one is nothing else but a solution of this problem here. You see this problem? But assuming that instead of air, we have a dielectric. So if this were filled by a dielectric, all of it, for a second, and you would repeat the solution of the problem, then here, instead of epsilon naught, you would have epsilon. That will be the only difference. Okay? So, but here we solved it with epsilon naught. So you go here, and I have put here the solution for you. So what I would like you to do as a practice problem is to find this, I say here, find this relation by solving this problem, following exactly what I've done here. Just repeat the solution, but with epsilon instead of epsilon naught. And then you're gonna find exactly this, what I have here for you, where A is the area of this parallel plate. Now, what I would like you to do here, where we're gonna spend a little more time, is if the parallel plate capacitor had two dielectrics. In this case, what happens if it has two dielectrics? So first of all, let me do here something so you can see. All right, so you have a parallel plate capacitor that looks like that, one plate, another plate, okay? And then you have a positive charge here because you put a voltage source. All right, positive charge here, all of this Q, area A, it's a square obviously. Negative charge here, also minus Q, it's the same, the two charges that accumulate minus Q, of course area A. And here what happens is that I have two separate dielectrics. Okay, one is this dielectric, and let me do it a little bit like this. And the other one is dielectric to a different one. Let's do this. All right, so one, the blue one has epsilon 1, the other one has epsilon 2. Not only I give these two, epsilon 2 here, but also it has a thickness H2. And the other one is epsilon 1 and has a thickness H1. H1 here and H2 the other one. All right. Now let's look a little bit in what happens with the field. The field is going to be normal, obviously. All right. The field is normal for two reasons. One, because without the dielectrics, that field ideally would be normal. So without any of the material, the field will have to be here. And second, because introducing the material does not really change the interface, a planar interface like that is not going to introduce any extra components to the electric field, especially because the flux, so D here, if this is D1 in the one medium, and if it is D2 in the second medium, the flux is continuous, the normal, all right? So the flux here, or initially without the material, would have been normal. So D, if this is the end, the direction, this one here, it's the normal to the interface, to the conductors, and of course normal to the interface, all right, because the interface is parallel. Then D N1 equals to D N2 at interface. All right, so if you consider that, then practically you find that D1 and D2 in this problem, it will be Dn, which is the initial, will be Q over A. That will be because of Gauss's law, all right? So the Dn, as we have found in the previous problems, without any dielectric in there, it would have been Q over A. But because you have two dielectrics, that gives you an electric field in the upper area here, which is Q over A, but divided by epsilon 1, all right? Because there is a relationship here between E1n, in fact, I should write it different way so you can see it. The relationship is D1n equals epsilon 1 En1 and Dn2 equals epsilon 2 En2. And because Dn1 equals Dn2, then you have these two expressions for E. Knowing the electric field, then I can go and find from the electric field, and not necessarily what I have here, we'll see something that later. What do we know? We know, if I were to erase this, because we don't necessarily need that for now. Oops, why did this go away? Ah, I know why it did not go away. Not that it's incorrect, but I don't want to confuse you for a moment. This is correct what I have to say, what I wrote, but I don't want to confuse you for a moment. The only thing that we know, I proved here there are no tangential components. So forget that for a moment, all right? It's not incorrect, it's correct, and we'll come back to this next time. But what I would like to remind you is the following, that we know that E is minus gradient of V. And because of that, here we can find the voltage difference in this problem. So the problem has A, B, and C. We can find the potential difference between the two conductors by applying this relationship here. And therefore you find this, that V1 minus V2, V1 is the voltage on the upper conductor. This is V1. One conductor, 2. The voltage at 1 minus the voltage at 2, which is the difference, and therefore, I mean, the potential at 1 minus the potential at 2, which the difference gives us the voltage across the two conductors, is equal to this. So that gives you the voltage as a function of Q, and then the geometry. And from C, which is the capacitance, the total capacitance of Q over V, which is Q over V, it gives you a very interesting relationship here. I want you to read this, and we are going to cover it again on Wednesday, but I want you to see what happens. If you have two layers, horizontal, that fill a parallel plate capacitor, this is equivalent to having two capacitances in series. So it's very interesting that without even doing the electric field derivations, then you can remember that if I have a material that cuts, a material that fills the parallel plate capacitor like this, so the electric field goes through the interface vertically, then that is equivalent to having two capacitors in series. And that's what you get, which is an extremely, that in fact, the last one that shows you this is like you had two of these capacitors in series, or is equivalent to having one parallel plate with H1 and epsilon 1 connected with another parallel plate, H2, E2. So this is one capacitor, and then in series with another capacitor. This is called the circuit equivalent of a parallel plate capacitor which is filled with two dielectrics. So that is what I wanted to cover today. And on Wednesday, before we introduce magnetostatics, I will do another similar, now where the materials are are vertically divided. Very similar approach. And then we'll do a general. So we'll solve these two problems, and then we'll move on to magnetostatics. Any questions?
Professor,
Yes.
previously you said that the charges tend to go to the edge of
Yes.
a squared
Yes.
charge or capacitor.
Yes.
So what about like on the edge of these two
Yes.
capacitors? Like,
So we have ignored it for now. So we call them an ideal parallel plate capacitor. And I will write it, I will add it, so I put it here for myself. Ideally, yes, and I mean ideally. In reality, yes, the charges go to the edges. However, I have to tell you that if the area of the capacitor is so much larger than the separation between the two plates, then these effects here are minimal because of the accumulation of charges. So the extra edge effect, which adds some capacitance to the problem, and because it's in parallel, I will talk to this, I don't want to talk to this right now, but for you, I have to say, since you asked me, I don't know if you are in the honor section, you're asking this question, but the electric field ideally goes like that. In reality, because of the charge distribution at the edges, it will go like this. All right? Now, these additional lines here introduce an additional capacitance. So the equivalent circuit model for this capacitor is the capacitor we found now, assuming an ideal condition without the edge effect, in parallel with two small capacitors from the edge effects, from the two edge effects. But these capacitances are so much smaller. What happens when capacitors are in parallel? That the total capacitance is the sum. So 2C effect, edge effect, plus C. But the C edge effect, it's so much smaller than C, so that we ignore it. So we assume that C total equals C, and that if this is the width W or the area, if the area, for example, is much higher than H squared, if the area is much higher than H squared, or if H or W is much higher than H, but the first one is more accurate rather. The first one, I would say, or the second one, anyways, for our purposes. If this case happens, then this C edge capacitance is so much smaller, so we can ignore it. Is that, does that explain?
yes. Thank you.
You're welcome. Any other questions? Okay, one thing before you go, I will turn on an exercise. Okay, before you go, I have to, it's like a regular exercise. You will have until Wednesday. I will turn it on. Go here, howdy, there. Come on, this. Okay, and go to this. Come on. and go to exercises. And exercises, I will turn this one off. No, okay, I got this off. I will, no, with that, I will turn this off and assign as review. And we'll go to this one and I will turn this on. It's on a capacitor without dielectric. So it asks, okay? So this is an exercise for you to do until Wednesday, okay? It's on a capacitor without multiple dielectric, just an ideal parallel plate capacitor, okay? You guys have until Wednesday. All right, we'll see you then. Goodbye.
Thank you, Professor.
Yes, bye.
Have a good day.
Goodbye.